Hey guys, welcome back to a new video. In this session we're looking at electrostatics. In particular, we'll be solving exercises step by step on how to use the Coulomb formula in real physical problems. As always, the timestamps can be found in the description, and if you have any questions along the way, let me know in the comments down below. Before we get into the first exercise, let's remind ourselves what the Coulomb law actually means. It's basically an expression that quantifies the force of attraction or repulsion between two charges at a distance from each other. Let's say we have two charges, Q1 and Q2, and they are separated by a distance r. The force F felt by each charge is equal to the fraction of the product of the two charges in the numerator divided by the distance r squared in the denominator. And this peculiar k in front of the fraction basically takes care of the units, because force has units of Newton, charge has units of Coulomb, and distance is of course expressed in meters. Thus we see that on the right hand side of the equation we have units Coulomb squared divided by meter squared, and on the left hand side we simply have Newton. Therefore we need this k to take care of converting the units. Thus k needs to have the units of Newton meter squared divided by Coulomb square. And more specifically, k is equal to 8.99 times 10 to the power of 9 Newton meter squared divided by Coulomb squared. More details about the theory of electrostatics I will leave for a future video. Let's now go into the first exercise. In the first exercise, we're going to be calculating the electrostatic force experienced by the two electrons inside of a helium atom. And let's refresh your knowledge about the helium atom. So the nucleus exists of two positively charged protons and two neutrally charged neutrons. And around this nucleus, we have two negatively charged electrons. And in this exercise, we will be looking at the very specific case where the electrons are as far away from each other as possible. This means when they are in line with the nucleus and the other electron. Now this is a very limited and classical picture of the helium atom. And in a future video, we will be looking in detail at a quantum version of the helium atom, which is much more accurate. And from this quantum version, we will derive that the distance between the two electrons in the s orbital, or the diameter of the s orbital, is approximately equal to 30 picometers. And 1 picometer is 10 to the power of minus 12 meter, which is, so what do we have as a given? We have that the distance between the two charges is approximately equal to 30 picometer, which is equal to 30 times 10 to the power of minus 12 meter. We know that our charges, Q1 and Q2, are actually equal to each other because we're considering the Coulomb force between two electrons. And the charge of an electron is minus 1.6 times 10 to the minus 19 Coulomb, so also a very small number. And then of course we know that our K, our conversion factor, is 8.99 times 10 to the power of 9 Newton meter squared divided by Coulomb squared. And these are our givens. And with this information, we will first look at the following scenario, where we absolutely do not have a nucleus and only consider the Coulomb force between two electrons at a distance from each other that is equal to the diameter of a helium atom. We know that the Coulomb force is equal to this conversion factor K times the fraction between the product of the two charges divided by the distance between them squared. So we can simply fill this in now as being 8.99 times 10 to the power of 9 Newton meter squared divided by Coulomb squared times, and then we get this fraction. And in the numerator, we simply get the charge of an electron squared, because Q1 and Q2 are equal, so we simply get Q squared. This becomes minus 1.6 times 10 to the power of minus 19 Coulomb squared, and we divide by the distance squared. So we divide by 30 times 10 to the power of minus 12 meter squared. And before we dive into this calculation, we first check our units and to see whether we indeed get the units of force, which is Newton. We see that this meter square here and this meter which get squared cancel each other out, so they already drop. The same can be said for this Coulomb square in the denominator and this Coulomb here, which get squared as well. So these also drop out. And well, this is exactly the reason why we needed this K in the first place, because we see that we are left with simply the unit of force, which is Newton. And what we will do now is some kind of a trick with calculating with these difficult terms of powers of 10. We can calculate this by simply separating the numbers that we have, so 8.99 minus 1.6 and 30, and separating them from these powers of 10. And this simply becomes 8.99 times minus 1.6 squared divided by 30 squared. And now we simply multiply this with all of the factors of powers of 10. So we have 10 to the power of 9, which comes from here. We multiply this with 10 to the power of minus 19 squared, which comes from this term. And we simply divide this by 10 to the power of minus 12, which we also have to square. And now we can simply calculate that for this first term, we get 0.026 approximately. And for the term where we have these powers of 10, we simply use the fact that x to the power of a times x to the power of b is equal to x to the power of a plus b and the related relations that we have. So we have 10 to the power of 9 times 10 to the power of minus 38, because minus 19 times 2, because this whole thing is squared, is minus 38, divided by 10 to the power minus 24. Since again we have this minus 12 times 2, because it's squared. This simply becomes 0.026 times 10 to the power of 9 minus 38 plus 24, because this minus 24 is in the denominator, which means that it becomes a plus 24 in the numerator. And our final result will be 0.026 times 10 to the power of minus 5. And at this point, it becomes clear that I forgot something, and you probably have spotted it already. I forgot that we are dealing with a force, so we need the units of a force, which is Newton. And this Newton, of course, comes from here, which, as I said, I forgot. And we can still rewrite this result as 2.6 times 10 to the power of minus 7 Newton. And something important here to also notice is that because this is a number that is positive, so larger than 0, we see that this force is repulsive, which makes sense because two electrons have the same charge and of course will experience a repulsion force from each other. Let's now go to the second part of this exercise, where we also take into account this positive charged nucleus. And we see that the distance from the electron to the nucleus is of course half the distance between the two electrons. So this distance will be around 15 picometers. So let's see what we get as a result for this case. And a first step in this scenario is to realize that we're dealing with multiple charges here, and thus multiple forces. The first force is of course the repulsion force between the two electrons. And this one we calculated in the previous exercise to be 2.6 times 10 to the minus 7 Newton, which was a repulsive force. Now, however, we will have to calculate the force between the positive nucleus and the negative electron. And this force we still need to calculate, but we already know that this will be an attractive force because we have two positive charges in the nucleus and one negative charge as the electron. So to calculate this force, what are our givens? We have that the distance this time is 15 picometers, which is of course 15 times 10 to the minus 12 meters. We know that our charge 1 is simply the electron, so this will again be negative 1.6 times 10 to the minus 19 Coulomb. Now for the positive charge, we have the charge of two positrons. And because we know that the charge of a single proton is simply the opposite of the charge of a negative electron, we know that for the charge of the nucleus, we get 2 times plus 1.6 times 10 to the power of minus 19 Coulomb. And again, we have K, which is equal to 8.99 times 10 to the power of 9 Newton meter squared divided by Coulomb squared. And these are the givens for this scenario. And now we can very simply calculate the electrostatic force between our nucleus and our electron, which is equal to 8.99 times 10 to the power of 9 Newton meter squared divided by Coulomb squared, which is our K. And we multiply this with a large fraction. Within the enumerator, we have the product of our two charges. So we have our first charge, which is the charge of an electron, so minus 1.6 times 10 to the power of minus 19 Coulomb. And we multiply this with the charge of the nucleus, which is 2 times plus 1.6 times 10 to the power of minus 19 Coulomb. And we divide this, of course, by the distance between these charges, which is 15 times 10 to the power of minus 12 meter squared. And again, what we first do is we look at the units. So again, we see that meter squared gets cancelled with this meter squared. And now we see that this Coulomb squared cancels with 1 Coulomb unit from the electron and 1 Coulomb unit of the positive nucleus. And we're left with Newton right here, which at this point we will not forget. Again, using the same tactic of separating the numbers and the powers of 10, we get 8.99 times minus 1.6, which comes from the negative electron, times 2 times 1.6, which is the charge of the positive nucleus, divided by 15 squared, which is the distance between the nucleus and the electron. And as the second term, we of course take all of the powers of 10. So we have 10 to the power of 9 times 10 to the power of minus 19 times 10 to the power of minus 19 divided by 10 to the power of minus 24. And at this point, we do not forget that we have a unit Newton. This first term turns out to be minus 0.19. And we already see here that a minus sign pops up, which indicates that we're dealing with an attractive force. And then looking at the term with the powers of 10, we can again use the property of exponents. So we get 9 minus 19 minus 19 plus 24, which is minus 5. So we get times 10 to the power of minus 5 Newton, which can again be rewritten as being minus 1.9 times 10 to the power of minus 6 Newton. And this is, as we can see, an attractive force because we have a minus sign in front of it. And at this point, we're still not done because we've now calculated two forces. So we calculate the force of the electron-electron repulsion, which we did in the previous exercise. And we now calculate the force between the positive nucleus and the negative electron. So we still have to add these two up in order to get the final force experienced by the electron. So we get the total F is equal to the force between the electron-electron plus the force between the nucleus and the electron, which is equal to 2.6 times 10 to the minus 7 Newton minus 1.9 times 10 to the minus 6 Newton. And of course, this minus sign comes from the fact that we have an attractive force. We immediately see that the attractive force between the two positive charges and the one negative charge is much larger than the repulsive force between the two negative charges. Now, why is this such a difference? Well, first of all, there were two positive charges instead of one negative charge. This on its own would double the magnitude of the force. And the second factor, which has a much larger influence, that the two positive charges of the nucleus are half as close to the electron as is the other electron. And since we square the distance in the denominator, bringing a charge half as close as it was will quadruple the force it acts on our charge. So in total, the attractive force between the two positive charges of the nucleus and the electron will be 8 times as great as the repulsive force between the two negative electrons. Taking this difference, we find that the final force experienced by the electron is minus 1.64 times 10 to the power of minus 6 Newton, which is obviously an attractive force. And this solution to our exercise gives us something interesting to think about. If the net force on an electron in a helium atom is an attractive force to the nucleus, then what stops it from just simply colliding with the nucleus? Why is a helium atom stable? And we will answer this in detail in upcoming videos, both classically and quantum mechanically. In the second exercise, we consider the following scenario. Let's say we have 3 charges, 2 positive charges and 1 negative charge. And these charges are arranged in such a way that they form the corners of a right-angled triangle. What we further know is that the positive charges both have a charge of 3 nanocoulombs, and that the negative charge has a charge of -1 nanocoulomb. And to remind ourselves, 1 nanocoulomb is equal to 10 to the power of -9 coulomb, so 1 billionth of a coulomb. What we further know is that this distance is 10 micrometers, and this distance is 5 micrometers. And let's remind ourselves that 1 micrometer is equal to 10 to the power of -6 meter, so a millionth of a meter. The goal of this exercise is to determine the total force that this positive charge experiences. So it will experience an attractive force from this negative sign and a repulsive force from this positive charge. In order to tackle this problem, we start with drawing a coordinate axis. So we have an x-axis and we have a y-axis. In the origin, we put our negative charge, and our positive charges are distributed like this. And of course, we see that we indeed have a right-angled triangle. And like I said, the goal of this exercise is to find the net force that is exerted on this positive charge. And we see that this will be a sum of an attractive force due to this negative charge right here, and a repulsive force of this positive charge right here. And then the total force will be, of course, the vector sum of these 2 forces. However, we see that we have a trade-off right here, because we don't know which of these 2 forces, either the attractive force or the repulsive force, will be larger. The attractive force comes from a negative charge, which is closer to our positive charge. However, the repulsive force comes from a positive charge, which is further away. However, it has a larger charge. So at this point, we cannot say what the ratio will be between the magnitudes of the repulsive force and the attractive force. And therefore, we cannot really know how this total force vector will look like. So what we will have to do in this exercise is calculate these 2 forces, F1 for the attractive force and F2 for the repulsive force. Let us consider the attractive force first. And we know that in order to calculate this force, this magnitude of this force, we need 3 pieces of information. The first charge is equal to -1 nanocoulomb. And we know that the second charge, the positive charge, is equal to 3 nanocoulomb. And we know that the distance between these 2 charges is indeed equal to 10 micrometers. So R is equal to 10 micrometers. And these are the 3 pieces of information that we need in order to fill in our formula that we know to calculate the magnitude of the force between these 2 charges. But before we do so, let's first rewrite these quantities. We know that this is -1 times 10 to the power of -9 coulomb. We know that the positive charge is 3 times 10 to the power of -9 coulomb. And we know that 10 micrometers is equal to 10 times 10 to the power of -6 meters. And at this point, we can completely fill in the formula as we did before. So we know that F1 will be equal to this conversion factor, so 8.99 times 10 to the power of 9 Newton meter squared divided by c squared, multiplied by this fraction. And in the enumerator, we have the product of our 2 charges. So -1 times 10 to the power of -9 coulomb, multiplied by 3 times 10 to the power of -9 coulomb. And in the denominator, we have r squared, which will become 10 times 10 to the power of -6 meters squared. And as always, let's check our units. This meter square cancels with this meter because it is squared. This Coulomb squared cancels with 1 Coulomb here and 1 Coulomb there. And we see that we are indeed left with the power of force, which is Newton. Let's now, again, to do this calculation, use the trick of taking together all of the numbers. So for the numbers, we have 8.99 times minus 1 times 3, which are the two charges, divided by 100. And this 100 is basically this 10, which we have to square. For the powers of 9, we have 10 to the power of 9 coming from our k, times 10 to the power of minus 9 times 10 to the power of minus 9 coming from our two charges. And we divide this by 10 to the power of minus 12, which is of course 10 to the power of 6, which we square. And we get a result which is minus 0.27, which comes from this term. And we see already that we have a minus sign, indicating that we have an attractive force, times, and now let's consider the terms with the powers of 10. 9 minus 9 is 0, minus 9 is minus 9, and plus 12, because a minus 12 in the denominator becomes a plus 12 in the numerator. So we have minus 9 plus 12, which is of course 10 to the power of 3. And we should not forget our units Newton. And we already have a first result, which is minus 0.27 times 10 to the power of 3 Newton for our first attractive force. This means that we already have one force down, this attractive force between the negative charge and the positive charge. So let's now look at the other force, the repulsive force between the two positive charges. We know that both charges have a charge of 3 nanocoulombs, so that's already a given. However, in contrary to the previous force, we see that we don't yet know the distance between the two charges. However, because we know that this is a right-angled triangle, and we know that this distance is 5 micrometers, and this distance is 10 micrometers, we can use the Pythagorean theorem to also determine this distance, which will be r, which is what we need in order to use the Coulomb formula. So let's do that right now and focus on the second force. We know that Q1 is equal to Q2, the two charges that we're looking at, which are both equal to 3 nanocoulombs, which is of course 3 times 10 to the power of minus 9 coulombs. And then for the distance, we can use the following. So let me redraw this right-angled triangle. We know that this is the right angle. This is 5 micrometers. This side is 10 micrometers, which allows us to calculate this r with the help of the Pythagorean theorem. Because we know that r squared is equal to 10 micrometers squared plus 5 micrometers squared, which turns out to be 125 micrometers squared. And thus we know that r is the square root of 125 micrometers. And because we know that 1 micrometer is equal to 10 to the power of minus 6 meters, we know that r becomes the square root of 125 times 10 to the power of minus 6 meters. And at this point, we have all of the information we need to fill in our formula to calculate the magnitude of the repulsive force. So we get that F2 is equal to our converting factor, so 8.99 times 10 to the power of 9 Newton meters squared divided by Coulomb squared, multiplied by this long fraction. Within the numerator, Q1 times Q2, the product of our two charges. However, because we know that Q1 and Q2 are equal to each other in this case, we simply get 3 times 10 to the power of minus 9 Coulomb squared. In the denominator, we have r squared. And for r squared, we of course have 125 times 10 to the power of minus 6 meter squared, where we already squared this square root of 125. Looking again at the units, we see that everything checks out. The meter squares cancel out and the Coulomb squares cancel out. And we are of course again left with 1 Newton, which is the unit of force. So that checks out. To calculate this, we again gather all of the numbers together. We get 8.99 times 3 squared divided by 125, and the term with all of the powers of 10 gathered becomes 10 to the power of 9 times 10 to the power of minus 9 times 10 to the power of minus 9, where this comes from our k factor and these two come from our charges, divided by 10 to the power of minus 12, because 10 to the power of minus 6 squared becomes 10 to the power of minus 12. Running this through a calculator, we get 0.64 times then all of the powers of 10. 9 minus 9 gives 0, and minus 9 plus 12, because a minus 12 in the denominator becomes a plus 12 in the numerator, which becomes minus 9 plus 12, which gives 10 to the power of 3. And of course, we should not forget our units, which is Newton. And we already have our second result, which is the magnitude of the repulsive force. And this of course checks out because this is a positive number. And at this point, you might think that we're entirely done because we've calculated the magnitude of our two forces. So now we simply add these two up and we have our final force. However, this is of course true, but what we end up with is the magnitude of our final force. We don't really know in which way it points. Let's look at our original sketch again. We see that we have calculated the magnitude of F1 and the magnitude of F2. However, we don't really know in which way they point. Well, for F1, we know that it points in the negative y direction, but for F2, we don't quite know in which direction it points. And therefore, we don't know in which direction our final force will point. In order to have complete information of our final force, we need to have the force vectors of both of the forces of which we've calculated the magnitudes already. This means that for both of these forces, we need to get the vector components from their magnitude. And I've made a dedicated video on how to get the vector components from vectors. So if you're unfamiliar with this topic, I advise you to first watch that video. However, in this video, I will of course go through this procedure step by step. Let's first focus on our attractive vector F1, because we see that this vector F1 does not have an x component and points entirely in the negative y direction. So let's see what this gives us. So for F1, we have 0 for the x component, and this means that the entire magnitude of our vector, which we calculated, will have to be in the y direction and in the negative y direction. So we've calculated the magnitude of this vector F1, and we found it to be minus 0.27 times 10 to the power of 3 Newton. And this is already the result that we have, because this is the complete vector of this attraction force between the negative and the positive charge. Now for the repulsive force, things will get a bit more complicated, because we see that it has a component in the negative x direction and a component in the positive y direction. So what we need to do now is to get these components from the magnitude that we've calculated already. And to do this, let's first draw a straight line which is parallel to our x-axis. This line allows us to define the angle alpha. And we see that this alpha is closely related to the x and y component of our vector, namely in the following way. We know that the x component of our force vector F2 will be equal to the magnitude of the vector, which we've calculated already, multiplied by minus the cosine of alpha. And why a minus sign? Because we see clearly that the x component is in the negative x direction. And likewise, we know that the y component of our vector F2y is equal to, again, the magnitude of our vector that we calculated, multiplied by the sine of alpha. And this directly gives us the x and y components of our F2 force vector. Now, of course, before we can go on, you already see the problem here. We still need to find this angle alpha, which is not a direct given. However, we can find it by simple goniometric relations, because we see that this straight line here, which defines the angle alpha, is parallel to the x-axis. This means that by extending our force vector through our point, we see that this angle right here also is the angle alpha. And together with the fact that we know that this distance is 5 micrometers and this distance is 10 micrometers, we can use a very simple goniometric relation, namely that for this triangle, the tangent of alpha is equal to 10 micrometer divided by 5 micrometer. And because these two units cancel out, we see that this simply becomes equal to 2. This relation can be very easily inverted to find that alpha is equal to the inverse tangent of 2, which can be easily calculated to be 64.3 degrees. And there we already have our angle alpha, which can now be directly filled in our relations to find the x and the y components of our vector f2. Doing this, we find the following: that the x component f2x is equal to minus 0.28 times 10 to the power of 3 Newton. And for this, we use the fact that the magnitude of this vector we already calculated to be 0.64 times 10 to the power of 3 Newton. Likewise, the y component simply becomes equal to 0.57 times 10 to the power of 3 Newton. And this directly gives us the full information of the vector f2, which we are looking for. For the x component, we have minus 0.28 times 10 to the power of 3. And for the y component, we have 0.57 times 10 to the power of 3. And our units are, of course, Newton. And this finally allows us to make the calculation that we need, because we found that f1 is equal to 0 for the x component and minus 0.27 for the y component. And then we multiply this by 10 to the power of 3 Newton. And we found that for the F2, the repulsive force, that the x component is minus 0.28 and the y component is 0.57. And this also multiplied by 10 to the power of 3 Newton. And now we can add these two vectors component-wise to find the resulting vector, which then becomes the following. Our final result, F total, is equal to, for the x component, minus 0.28, and for the y component, 0.80, multiplied with 10 to the power of 3 Newton. And this is our final result. And this brings us to the end of this video. And I hope that you're now more familiar with how to solve exercises on electrostatics. As always, if you have any questions, leave a comment in the comment section below and I will be sure to answer it. If you learned something new, give this video a thumbs up, and if you want to get notified by future releases, consider subscribing. And with that, I thank you guys for watching and I will see you guys in the next one. Bye.